I'm the chairman of the first talk, which is the award lecture by the C.S.Hsu award lecture by Professor René Lozi, who was awarded this prize this year, 2024. First of all, let me tell you who was C.S.Hsu. Most people do not know him. He's an engineer, well-known engineer from China. He was born in Beijing. He was educated in Suzhou, Jiangsu province, and later he moved to the United States, and he was professor of applied mechanics in University of California, Berkeley. He made strong contributions to vibrations, oscillatory phenomena, and nonlinear dynamics at large, especially the method of cell-cell mapping. We have, years ago, decided to organize this award, honoring C.S.Hsu award. And as I said, this year, one of the winners, there are two, is Professor René Lozi. Professor René Lozi is a mathematician from France. He has been working almost all his life in different techniques in applied nonlinear dynamics, in particular in maps, different equations. He's well known for his map, which is called the Lozi map, similar to the Henop map. Very recently in the Journal of Difference Equation and Applications appeared a special issue on the Lozi map. He has collaborated with many relevant scientists. In particular, comes to my mind Professor Leonid Professor Leon Chua, Professor Won Chen, who is here present, and many others. As far as I know, he made a state thesis with Professor René. Professor René was very well known in the world of mathematics for his theory, for his catastrophe theory. That was before the past of nonlinear dynamics. Catastrophe theory was gave a big push by Professor Vladimir Arnaud, very well known for, I guess, for everybody. And he's also, let me just finish by saying that besides mathematics and nonlinear dynamics, etc., he's very interested in many things beyond mathematics, and within mathematics, something which I consider also very important, the teaching of mathematics. So, please, you can.
Thank you, Professor Dieudonné. It's a great honor for me to give this first talk in this great conference. And I will thank all the organizers to invite me to give this talk in the conference. And at the end of my conference, I will pay my tribute to Professor Hsu, who is an important professor who inspired me 30 years ago in dynamical system, discrete dynamical system, not only discrete in time, but also discrete in space. This is very important. I will give a few minutes about the importance of Professor Hsu. My talk is not very technical, it's more historical talk, because when you are old, I mean, it is important to have a view of what happens 50 or 60 years ago. And my problem was, do science, or are they just a mathematical curiosity for 10 years, 20 years, or not? This is important when you are young and you begin to do research, to try to find a way to continue your research for your life. And now there are new domains like fractal dynamics and artificial intelligence and many others that you have when you are young to think what I will do. When I began my PhD, I was working on bifurcation theory. Bifurcation theory at this time was not well known. And my first advisor, Professor Jean-Alexandre from Torino University, said to me, you will see in 10 years bifurcation will be very common. It was true. And thanks to him, I was doing my PhD, the first PhD in France about bifurcation theory. Then I will speak about some historical part of the dynamical system. Of course, this is only a part of this big conference because you can have chaos on discrete dynamical system, on ordinary differential equation, but there are many professors working in chaos in PDE, partial differential equation, and Professor Jean. And I cannot mention everyone in this large field of research, but I will focus on discrete dynamical system and ordinary differential equation system. And let me speak about the dawn of chaotic dynamical system from the early beginning to nowadays. And I have to say that in the history of chaotic iteration, which is the equivalent to discrete dynamical system, and chaotic differential equation, continuous differential dynamical system, is strongly interwoven. At the beginning, the study of nonlinear dynamical is relatively recent with respect to the long historical development of early mathematics since the Egyptian and the Greek civilizations, and also Mesopotamian civilization and other civilizations. The beginning of the study can be trusted to the phenomenal work of Henri Poincaré, and the Poincaré map being an essential tool linking differential equation and methods. Concerning the iteration theory, one has to include in this field the research work of the French Gaston Julia and Pierre Fatou, related to one-dimensional map with a complex variable near 1 century ago. Gaston Julia was during the First World War, and there was a wounded at his nose. It is why he has a mask in this picture, and Pierre Fatou. But at this time, there was no computer. And their work stopped after 10 or 20 years ago because it was difficult to continue their research without computer. In France, in 1958, Igor Vygotsky, who was from Poland, and Christian Murat from France, they were close friends, began their mathematical research at this time and produced a considerable work on the matter. They proposed the theory of boxes in the box, for example. But I did not mention the work of Miranda. Miranda was inspiring those two guys. Among their discovery, we can emphasize on their family of attractors from an aesthetic point of view. I will show you a picture. Of course, it is only a microscopic point of view of what they have produced. We can mention the Chimera attractor. You see the formula, the reciprocal formula in 2 dimensions, which is sensitive to slight changes of parameter A and B. But the idea of the butterfly effect, everyone knows the butterfly effect introduced by Edward Lorenz, was not in the midst of the mathematician at this time. I show you these 2 shapes, not very different, but different. And you see that the difference is the small change in the value of A and B. A part of mathematical research, the first came from the work of Edward Lorenz, the meteorologist, who studied the René-Bénard problem in 1963. What is the René-Bénard problem? Is the motion of a flow emitted from below. If you are cooking and you put some oil and, for example, if you are doing a hot pot, you will see some convection in hot pot because the fluid, the water in the bottom is heated and it is lighter than the fresh water, and there is a motion. And Edward Lorenz studied this motion and put the physical coordinate system constant along y, and he did discretization of equation in Fourier series. And what is interesting is that he had a very small computer at this time. It was difficult to integrate the Fourier series, and then he cut the series theory with a very small number of modes, only 3 modes. This gave this 3 differential, ordinary differential equation, and for the value of sigma equal 10, rho equal 28, and beta 8/3, he found this attractor. And at this time, he discovered the butterfly effect because he had no time to wait for 2 days for the computing of the solution, and he stopped the computer and he resumed computation using the last value, but he introduced only 3 digits in the last value. He found different solution, very different solution. At this time, people, you have to remember that Lorenz was not mathematician or physicist, he was a meteorologist. And at this time, the people say, oh, it is a computer error. And this paper was not very well known until 1970. And in 1970, David Real and Floris Tekens introduced the theory of chaotic attractor and find that 7 years before there was this paper of Edward Lorenz. And then this paper re-emerged at this time and led to the Lorenz attractor. Now there are thousands of papers published on Lorenz attractor and on the butterfly effect. That is, if there is a butterfly moving in the part of the Earth, then it can be linked to our hurricane 1,000 miles away. But the Lorenz attractor was difficult to study because it was strongly dissipative, and Michel René, who was an astronomer is very, very simple map. But what was very stunning is that starting from any point to the basin of attraction of this attractor, you can have this figure here. And this figure, I have no time to explain in details, but if you see the square, you see 3 lines. But if you enlarge this square, each line is formed for many lines, and if you enlarge again, you find an infinity of lines. That means that this attractor has a fractal geometry. 2 years after, at this time, Michel was working at the observatory of Nice, which is 20 kilometers apart from my laboratory of mathematics. And I wasn't knowing Michel on this time, but I was working in numerical analysis and on the finite element method. That means in finite element method, you linearize every function in order to do computation easily. And I proposed a linearized version of this attractor. At this time, I think, okay, in 1 week, I can prove anything. But near 50 years after, many people are published. And I was very happy today to meet Professor René, who worked on this attractor. It's a great pleasure to meet you, Professor Jean, because I read your paper since 35 years ago. It's a great, great pleasure for me. And there was not only mathematicians or physicists or astronomers or meteorologists working on chaotic attractor. There was also chemists. And Otto Rosler, who is still living, was working on what it was called the chemical multivibrator in 1976, and produced this theoretical model where A, B, C, E, T are chemical products, and the arrow showed the interaction between this product. And then he was conducted to produce this model of attractor, which is well known. It is the Rosler attractor. In fact, there are several versions of the Rosler attraction. And why Rosler was trying to do research in chemics? It's because he was thinking that the Lorentz attractor was very far from the reality of the atmosphere. There was a metaphoric model and not very interesting for physicists. It was interesting for mathematicians, but not for physicists. And Rosler was thinking that it was better to start with 3 or 4 chemical products and to try to write the interaction between this product. And then he found a chaotic attractor. And in October of last year, we celebrate the 80th birthday of Otto Rosler in Toulouse with a great conference on chaos to application. In Japan, the Hirashi school with bicycle like Kensuke Ida, C.S.Hsu we will be able to talk in this conference, and Hiroshi Kawakami, a friend of mine, in the same period were motivated by the application of electric and electronic circuit and provide a mapping to see that changing slightly the value of the parameter u, you have different figure. I had the pleasure to work with Hiroshi Kawakami for several years. I met him in Fukushima, in Japan, in Kyoto, where I spent some months of research. And with Hiroshi Kawakami, I published the linear spiral attractor in 1992. This attractor is very simple and the model an electric circuit. The dawn of chaotic differential equation was the first beginning of, because I remember I published the attractor in 1992, but before, in 1918, there was a work of Arkady Kovsky, who will be the speaker, and Mikhail Rabinovich, who produced this circuit, electronic circuit here, and found a chaotic oscillation in this circuit, and the model of the current is very simple. But this model was not very popular because you see that the value of f of c is quite complicated. And 2 years after, Leon Schwartz, working in Waseda University at the laboratory of Professor Matsumoto, found a very simple chaotic circuit in 1983. This is the Schwartz circuit, and he found the Schwartz attractor. Why this is very interesting? It is because you see this function phi is piecewise linear. And when you have piecewise linearity, you lost differentiability at some point, or some length in this case, but you can study very well. And now, I don't know the number of papers published on the Schwartz attractor, and more interesting, Professor Nikolai Kuznetsov found an island attractor with his advisor, Professor Leonov, on Schwartz equation. Very interesting new method to find attractor far from the fixed point. And this is a new idea published maybe 15 years ago or 20 years ago, and this has to be explored again. The interest of the Schwartz attractor is that you can see the attractor on the oscilloscope. And we put the Schwartz attractor is a small circuit, electronic circuit, and you branch this on the screen of the oscilloscope, and you can find this attractor. And along these 60 years of history, there are some outstanding researchers, like Professor Tchaikovsky, we have time to explain the fundamental work of order of the natural number of Professor Alexander Tchaikovsky, who passed away 2 years ago, unfortunately. The Lorentz attractor, the real strange attractor who rediscovered the work of Lorentz. The important figure of Jean York, a friend of Miguel San who introduced, who coined the name of chaos in his famous paper with his student Lee. Period 3 implies chaos. The Rosenthal attractors, the Enom lab, Enom was in the defensor of my, not my PhD, but my habilitation thesis. The Vedic map from Nizhny Novgorod, Volga University, a good friend of mine also, the Schwartz attractor, there's all paper are good friend of mine. And since the last 60 years, many papers were published in pure mathematics or statistical physics concerning research on property of nonlinear maps and chaotic iterations, like introducing the new mathematical tool like entropy, or several kinds of entropy, ergodicity, Lyapunov, and Earth exponents, invariant measures like dimension, border collection, etc. However, application of nonlinear mapping in applied mathematics, engineering, physics, biology, economy began only 20 years after. And we can speak about secure communications, chaos to randomness. Randomness is not exactly chaos. At the beginning, people were thinking, okay, the chaos is equal to randomness. It's not exactly the same. And I will show you how to create chaotic pseudo-random generators. Cryptography-based chaos, this is very important now, cryptography. Hash function is the basis for Bitcoin or the euro money. Memory store, I will speak about the memory store invented by Joshua. Global optimization, like particle swarm optimization. Evolutionary algorithms, and also in human health and migraine disease, physiological control system, hypertension and cardiac dysrhythmia, cancer, and also economy. Thus, I will speak about the secure communication via chaotic synchronization. The first example of the use of chaos for cryptographic purpose goes back to the early 90s when Luis Pecora and Tom Carros found how to synchronize chaotic systems. This discovery was unexpected breakthrough for application. And the first reported experimental secure communication system, the chaotic synchronization used in Schur circuit, was built 2 years after, in 1992, with a master-slave Schur circuit. And you see you have the same circuit, but there is a link between both. And if you have a chaos produced by the first circuit, you can control the chaos produced by the slave circuit. The signal recurrent from this system, which use the Schur circuit, contains some inevitable noise, which degrades the fidelity of the original message. And with Leonchua, we found a way to improve this system by cascading the output of the receiver in the original system into an entire copy of the receiver. This idea is a simple idea in numerical analysis of relaxation. And I introduced this idea of relaxation and working with Leon Chua, who was visiting me at this time. We produced this couplet circuit, and of course, I can give you only an image of the duplicate of this coupling circuit, but we can improve this using 3, 4, 5 copies of the identical circuit. Now I switch to another domain. This is from a chaotic attractors to pseudo-random number generators. The rule, I said a few minutes ago that chaos is not randomness. Randomness, chaos, you have a chaotic attractor, and in a fast space, you have not spreading of all to spread all the iterate, you can use chaotic attractor, but you have to modify. There are several ways to modify. I wrote a paper in 2012 about the emergence of randomness from chaos. How I did this? I did this taking one-dimensional map, like for example the symmetric map, which is well-known, and copying several copies of this map with a small value of parameter epsilon, epsilon 1, epsilon 2, epsilon 3, and epsilon 4, with the value 10 minus 7, you are working with floating points, or 10 minus 14 with total precision number. And this ultra-weak copying is efficient in order to restore numerically the chaotic property of chaotic mappings, avoiding any numerical collapse. Because if you study the symmetric 10 maps, you have some unstable fixed point. Theoretically, they are unstable. But if you compute with a computer without being careful, you can have a collapse. And there is a professor Clausen, Peter Clausen, who found a good theory of the collapse of iterate. But with using this kind of coupling, coupling of one-dimensional map, you can recover interesting randomness. Another one is chaotic is mixing under sampling. That means if you are with this equation, you can mix the sequences obtained by the first, second, third component using the value of the last component. And how you do this? You check the value of the last component, and if this last component is between two thresholds, you decide T1, T2, you can choose the value of T1 and T2, and then you take the first component. If the value of the fourth component is between T2 and T3, you can choose the second component. And again for the third component. And of course, this is just an example. You can choose the more than 4 equation. You can choose more than 3 threshold, etc. And then you obtain very good pseudo-random number. I have to indicate that the random number are only produced by physical devices and not by mathematical formula. And when we use mathematical formula, we call this pseudo-random number. But pseudo-random number are in practice equivalent to random number. Another way is to couple time and logistic map. I say first that we have the temp map, which is well known, and the logistic map, which is known also. And it is possible to combine the temp and the logistic map, giving this formula. And you see the graph. This is on the left hand side, there is the logistic map. In the middle, you have the graph, temp map, and on the right-hand side, you have the temp logistic map. And coupling these temp logistic maps in using a ring network of one map, you can couple 10, 20 or more. One map, and of course, when you couple this map, you have to restrain the new p-dimensional map to the torus -1, 1, comma 1 at power p. And if you set the coefficient I to -1 to +1, you can obtain a very good pseudo-random number generator. Another way is using 2D chaotic pseudo-random generator. I show you very rapidly several combinations possible of chaotic map to obtain a pseudo-random generator. And you can use this map of the plane into the plane with the new injection mechanism which fits better the torus. I'll show you in this picture. You see that the red part, the upper red part is going to the green part. The lower red part, the right red part is going to the yellow part. And the lower part of the yellow part is going to the purple. And then you recover the rectangle. And it is the way to have an injection mechanism. And this gives you this kind of pseudo-random number. And these pseudo-random number are good for the NISTs. The approximate density function of this alternative map on the first plane, and on the right hand side you have the approximate density function for alternative map on the first delay plane. Of course, you don't limit yourself when you study this map to this plane, but you have also to check every component, combination of components to be sure there are no figure when you can recover the number obtained by random process. And we have done I work for 10 years about this pseudo-random generator. And of course now you have a multi-core processor in the computer. And the new computer have 1,000 or 100,000 of microprocessor. And we can do this experiment with a lot of computation of iterate. And we found that the pace of computation is very high. And when we use 5 components in a machine, which is not very efficient machine, it is simply using 8 processor, we can compute 2 billion of pseudo-random number per second. And since each pseudo-random number are computed in standard level of precision, it is possible to extract from each 50 random bits, the size of the bundle, being 52 bits for the precision floating point. And then you can produce 100 billion random bits per second. It is an incredible pace. And we try also Intel with 80 logical core, and you can produce 200 billion random bits per second. And you see that starting from chaotic attractor, combining this chaotic attractor in this special way, it is possible to have a very efficient method to have a pseudo-random bit generator. And there are many companies in the world obtaining millions of dollars sending pseudo-random for games, for Monte Carlo method, for many. And this leads to the new idea of chaotic cryptography. I published this book with my friend value, but also for generating hash function. Hash functions are very important for cryptocurrency, but also for your credit card. Your credit card is using hash function. And for Bitcoin, you know that the price of the Bitcoin is increasing. Now, I don't know, it's maybe $60,000. One Bitcoin. One Bitcoin was only $10 15 years ago. And the recent methods are not only mathematical, but they are implemented in FPGA cards. It is a work I did with my friend Jean-Alexandre and PhD student René from Tunisia, and Morsen Marshall, his advisor in the Tripoli University. And also there is a way to generate hash function. Hash functions are one of the most useful primitives in cryptography that play an important role in data security. This function is a one-way function that maps an arbitrarily finite large message data into a fixed-line hash value. This is on the left-hand side you see you have a message, hash function, and you have the fixed-line hash digits of this message. And then, if you want to compare two messages, you have not to compare the messages, you have only to compare the hash result of this message. And the way to obtain this message is a combination of chaotic system, you will see in the other side, and some electronic combination. And this, you see, the work of the mathematician is only a part of a more global work with electronic people and people doing control system. Another very important thing is memory store. Memory store was first found by my friend Jean-Alexandre, who was a professor of electronics in Berkeley University in 1971. And he found a new device, electric device, very interesting. I will show you what is this device. And this, it will be shut paper, but this was forgotten for 39 years or 37 years. But in 2008, there was a paper with the cover of Nature, the review Nature, in 2008, when people were studying nano element, nanotechnology, and found that to model this nanotechnology device, they found the only way was to use memory store theory. What is memory store theory? Some of you have done some very simple physical study in high school, and you know in high school that in electricity important is the current, which is in ampere, the voltage, volt, and the charge, in coulomb. What is less popular is the flux. Flux is in the Weber, and you can put on the 4 edge of the square. And if you try to see what are the side of the square, you have the electric energy, and they are stored in the capacitor. The magnetic energy is stored in a nickel. The thermal energy is stored in a resistor. It is when you are heating a room with a resistor, you produce thermal energy from electricity. But for many years, people were studying the three sides of the square, but not this last four. And Joshua said, oh, well, what happens here? This side. And then he found there is a device, we call this memory store, that is a resistor with memory, and he produced the theory of memory store. And now people are trying to find practical material to produce memory store, and there are hundreds of papers. I show you the paper with my name. It's important to do the publicity, but it is only one paper. And what is interesting is that this model by Professor Wang, Xu, and Zhang is that they use the model I propose, which is known as Lozi, but in 3D, with they introduce this sine function, and with this simple model producing chaotic operator, they can produce a theory of memories. One other important thing is chaotic optimization. I go very shortly. We can use chaotic sequences to improve the performance of evolutionary algorithms, and you can use chaotic optimization in industry. I showed my goal. Chaos is used to control PID controller with this equation. You can find chaotic operator in human health. For example, to control the progression of cancer, you can have this kind of continuous equation. You can find some paper work in economy, and you have a simple 2D map, and you can find a very interesting property of chaotic attraction. I will finish soon with two ideas. The first idea is that the complexity, to do parallel between complexity in life and mathematics. If you see the operation of the life on the earth, starting from prokaryote, eukaryote, bacteria, protozoa, fishes, plant, mammal, this is the very simplified model. You have humans, and you have scientists, of course. And if you do the parallel with mathematics, 40,000 years ago you have telemark, then number, geometry, function, differential equation, and let me show my favorite professor, C.S.Hsu, the self-fulfilled mapping. In 1998, my attention was caught by this book, the Library of Mathematics Department, and I was fascinated by the idea of considering dynamical systems with not only in time, but also in space, as Professor Xu introduced in this book, in the self-fulfilled mapping. And I have always found since then, since I became a researcher at CBRS in 1974, that mathematical analysis was too dependent on the notion of continuity and differentiability. And I tried, without success until now, to find an equivalent of the notion of continuity for discrete space. I think that is still a challenging but essential problem for calculation with computer computation. And in 2008, in the same spirit of the self-fulfilled map, but limited to one-dimensional dynamical system, I introduced the notion of global orbit pattern for dynamical system on finite set. But I can't find time to explain this method, which is very good to from the